Hello, and welcome to the Nocturnal Astronomer. This channel exists as a gentle companion for your quiet hours, whether you're drifting towards sleep, studying in the late evening, seeking focus during work, or simply finding a moment of relaxation in our chaotic world. I'm your host, Atlas Reed, and tonight we're going to explore one of the universe's most striking phenomena. Imagine a world where the sun never sets on one hemisphere, baking the surface in endless light, while the opposite side remains locked in perpetual frozen darkness. These are tidally locked worlds, places where the same face eternally gazes at their parent star, creating conditions so alien yet so mathematically inevitable that they represent perhaps the most common planetary arrangement in our galaxy. We'll journey through the physics that creates these strange configurations, visit real examples both in our solar system and beyond, and contemplate what existence might look like on these divided worlds. Let's dive in. Part 1, an intro to tidal locking. The concept of tidal locking sounds complicated, but you've witnessed it your entire life without perhaps realizing it. Every time you look up at the full moon, you're seeing the same lunar face that humans have gazed upon for hundreds of thousands of years. The man in the moon, the rabbit shape seen in Asian cultures, the various patterns we've ascribed to those gray plains and bright highlands, they occupy the exact same position they held when our ancestors first looked skyward. This isn't coincidence. The moon is tidally locked to Earth, rotating on its axis at precisely the same rate it orbits our planet. One lunar day equals one lunar orbit, both taking approximately 27.3 Earth days. This synchronization means the moon's far side, often incorrectly called the dark side, remains forever hidden from our direct view. Not until the space age, when Soviet probes first photographed those hidden plains and craters, did humanity glimpse what lies on the moon's opposite face. But what force creates this cosmic choreography? The answer lies in gravity's patient, inexorable influence. Tidal locking emerges from the same gravitational effects that create ocean tides on Earth. When two bodies orbit each other, the gravitational force is slightly stronger on the near side than the far side, simply because gravity weakens with distance. This difference, called a tidal force, stretches both bodies into slightly oval shapes. For Earth and Moon, our planet raises tidal bulges in the Moon's rocky body just as the Moon raises tides in Earth's oceans. These bulges create friction within the Moon's interior, and here's where the magic happens. Any rotation that doesn't match the orbital period means these bulges constantly shift position, generating heat through friction and gradually slowing the rotation. Over millions of years, this friction acts like a brake, slowing the smaller body's spin until it matches its orbital period perfectly. At that point, the bulges become stationary relative to both bodies, the friction ceases, and a stable configuration emerges. The smaller body now keeps one face permanently toward the larger one. This process operates throughout the cosmos wherever bodies orbit in close proximity. The timescale depends on several factors including the body's masses, their distance apart, and the composition of the smaller body. A close orbit and large mass difference accelerate the process. The Moon achieved tidal lock with Earth relatively quickly in cosmic terms, perhaps within the first 100 million years after its formation. But tidal locking isn't a one-way street. Earth itself is gradually becoming tidally locked to the Moon, though this process unfolds over billions of years. Currently, Earth's rotation slowly decreases, lengthening our day by about 1.7 milliseconds per century. In the distant future, if the sun doesn't expand and consume both bodies first, Earth would eventually show only one face to the Moon, just as the Moon now shows one face to us. At that point, observers on one hemisphere of Earth would see the Moon hanging motionless in the sky, while observers on the opposite hemisphere would never see the moon at all. The mathematics underlying tidal locking follow predictable patterns. Scientists can calculate how long a body takes to become tidally locked using equations that account for orbital mechanics and internal structure. For our moon, the calculation reveals that tidal locking occurred when the moon was much closer to Earth than today. The moon currently recedes from Earth at about 3.8 centimeters per year, a rate measured by bouncing laser beams off reflectors left by Apollo astronauts. This recession happens because tidal forces transfer rotational energy from Earth to the moon's orbital motion. As Earth's rotation slows, the moon's orbit expands. It's a beautiful example of conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling in their arms. Understanding tidal locking opens a window into planetary dynamics across the universe. Most moons in our solar system are tidally locked to their planets. The major satellites of Jupiter, Saturn, Uranus, and Neptune all show this configuration. Pluto and its moon Charon represent an even more fascinating case. They're mutually tidally locked, both showing only one face to each other, spinning together like partners in a cosmic waltz. This mutual lock creates a unique situation where Charon hangs motionless in Pluto's sky, visible only from one hemisphere, while Pluto similarly appears fixed in Charon's heavens. This represents the end state of tidal evolution, the final configuration where both bodies have settled into perfect synchronization. Part 2: The mechanism of tidal forces. To truly grasp tidal locking, we need to dive deeper into the mechanism that drives it. Imagine holding a rubber ball and squeezing it gently from opposite sides. The ball deforms, bulging outward at the top and bottom while compressing in the middle. This physical distortion resembles what happens when gravity pulls unevenly on a celestial body. The key insight is that gravity isn't uniform across an extended body. If you're standing on the side of the moon facing Earth, you experience slightly stronger Earth gravity than someone standing on the moon's center. Someone on the far side experiences even weaker Earth gravity. These differences might seem tiny, but across planetary scales, they become powerful sculptors of cosmic architecture. The deformation creates two bulges, one pointing toward the larger body and one pointing away. You might intuitively understand the near side bulge. Gravity pulls harder there, stretching the body toward its companion. But why does a bulge form on the opposite side? This seems counterintuitive until you realize that the moon's center is being pulled harder than its far side. The center tries to fall toward Earth faster than the far side can follow, effectively leaving the far side behind, creating a bulge through what's essentially differential acceleration rather than direct pulling. Both bulges exist simultaneously, creating an elongated, football-shaped distortion in what would otherwise be a sphere. Now imagine this distorted moon rotating. If the moon spun faster than it orbited Earth, these bulges would sweep around the moon like waves, constantly changing position relative to the surface below. Rock, unlike water, doesn't flow easily. As the solid body tries to rotate through these gravitationally imposed bulges, immense friction develops within the moon's interior. The rocky layers grind against each other, converting rotational energy into heat. This is the same principle behind rubbing your hands together to warm them. Motion creates friction, friction creates heat. In the moon's case, this internal friction acts as a brake on its rotation. The heating from tidal friction can be substantial. Io, Jupiter's innermost large moon, demonstrates this dramatically. Io orbits so close to massive Jupiter that tidal forces knead its interior like dough, generating enough heat to make Io the most volcanically active body in our solar system. Hundreds of volcanoes continuously erupt across its surface, spewing sulfur compounds that paint the moon in yellows, oranges, and reds. The heat source isn't radioactive decay, as in Earth's interior, but purely tidal friction. Jupiter's gravity constantly squeezes and releases Io as it orbits, and this rhythmic deformation generates tremendous internal heat. Io is already tidally locked to Jupiter, showing the same face to the giant planet, but its orbit isn't perfectly circular due to gravitational influences from other moons. This orbital variation means the strength of tidal forces on Io fluctuates, maintaining the heating even after rotational lock occurred. The rate at which tidal locking proceeds depends critically on distance. Tidal forces diminish rapidly with separation, following an inverse cube relationship. Double the distance, and tidal forces drop to 1/8 their former strength. This means moons orbiting close to their planets lock quickly, while distant moons might never achieve tidal lock during the current age of the universe. Consider Earth's moon again. At its current distance of roughly 384,000 kilometers, it locked to Earth within perhaps 100 million years of formation. But the moon formed much closer to Earth, possibly as near as 20,000 kilometers, where tidal forces would have been thousands of times stronger. At that proximity, locking might have occurred in mere thousands of years. The internal structure of the rotating body also matters enormously. A fluid body deforms easily, creating large tidal bulges with relatively little friction. These bulges can flow with the rotation, reducing the braking effect. A rigid, solid body resists deformation, creating smaller bulges but much more friction as it tries to rotate through them. Interestingly, this means solid bodies can lock faster than fluid ones under certain conditions, despite deforming less, because the friction is more effective at stealing rotational energy. The moon, being a solid rocky body, experienced efficient braking. The presence of internal oceans or molten layers complicates this picture, creating scenarios where different layers experience different torques and can temporarily decouple from each other. Temperature affects tidal locking too. Hotter materials deform more easily than cold ones. A body with a warm, partially molten interior will develop larger tidal bulges and experience different friction patterns than a cold, rigid body. This creates feedback loops. Tidal friction heats the interior, making it more deformable, potentially increasing the bulge size and the friction itself. Eventually, an equilibrium establishes itself where heat generation balances heat loss to space. For the moon, this equilibrium settled long ago, and its interior cooled substantially after achieving tidal lock and moving away from Earth, reducing the tidal heating. Scientists model these processes using complex mathematics that tracks energy transfer between rotation and orbit. The equations account for the body's moment of inertia, how its mass distributes around its rotation axis, the tidal quality factor, a measure of how efficiently the body dissipates tidal energy as heat, and the orbital parameters. Solving these equations for various scenarios reveals the timeline to tidal lock. For Earth's moon, models suggest locking occurred relatively early in lunar history. For Mars' moon Phobos, orbiting much closer to Mars than our moon orbits Earth, the locking timescale was extremely short, perhaps only a few million years. Phobos not only locked quickly but continues to spiral inward toward Mars due to ongoing tidal interactions, and will either crash into Mars or break apart into a ring system within about 50 million years. Part 3. The Moon, our tidally locked companion. Our moon serves as the perfect laboratory for understanding tidal locking because we've studied it intimately, sent humans to walk its surface, and measured its properties with exquisite precision. The moon's tidal lock creates the familiar pattern we see every night when we look up. The near side, facing Earth, contains the dark plains called Maria, formed by ancient volcanic eruptions that filled giant impact basins with solidified lava. These Maria create the patterns humans have interpreted as faces, rabbits, or other figures throughout history. The far side, hidden from Earth, has dramatically fewer Maria and more heavily cratered highlands, a difference that puzzled scientists until lunar missions revealed it. Why should the near and far sides look so different? The answer probably relates to the moon's tidal lock itself. When the moon was young and still cooling, Earth's proximity and gravitational pull may have affected how the lunar crust formed. The near side, facing Earth, might have experienced different thermal conditions than the far side. Some theories suggest Earth's heat radiation warmed the near side, keeping its crust thinner and making it easier for later volcanic eruptions to break through and create Maria. Other models propose that the moon's center of mass doesn't coincide perfectly with its geometric center, sitting slightly offset toward Earth. This offset would create a thinner crust on the near side naturally, again making volcanic flooding more likely there. The jury remains out on which mechanism dominated, but the striking difference between hemispheres almost certainly connects to the tidal locking process. The moon's synchronous rotation means one lunar day equals one lunar month, both lasting about 27.3 Earth days. But here's a subtlety worth appreciating. Because the moon orbits Earth while rotating, an observer on the moon experiences day and night cycles, just extended ones. At any point on the lunar equator, the sun rises, climbs slowly across the sky over about 13.6 days, sets, and then darkness reigns for another 13.6 days before sunrise returns. The only exception is the poles, where the sun circles the horizon, never rising high in some deep craters and never setting on some ridge peaks. These permanently shadowed craters contain water ice, protected from solar heat by eternal darkness, while nearby peaks experience near constant illumination, making them prime candidates for future lunar bases. From Earth's perspective, we see the moon go through phases as the sun illuminates different portions of the hemisphere facing us. But from the moon's perspective, Earth hangs nearly motionless in the sky. An astronaut standing on the near side would see Earth looming large, going through phases opposite to the moon's phases as seen from Earth. When we see a full moon, an observer on the moon sees a new Earth, completely dark. When we see a new moon, they see a full Earth, fully illuminated. This Earth would drift slightly in position due to libration, small wobbles in the moon's rotation and orbit that let us peek around the edges, but it would never rise or set. It would simply hang there, slowly changing phase, a beautiful blue and white marble against the black sky. An observer on the moon's far side would never see Earth at all. For them, Earth doesn't exist in the sky, removed from view as completely as if it orbited another star. They would see only stars, the sun, and occasionally other planets. The psychological impact of such permanent isolation from humanity's homeworld struck the Apollo 8 astronauts powerfully when they became the first humans to orbit the moon and witness the far side directly. As they swung behind the moon, Earth disappeared below the lunar horizon, and they became the most isolated humans in history, cut off even from radio contact with every other person in existence. The experience of looking out at the far side's ancient, battered highlands, knowing Earth lay completely hidden beyond the horizon, profoundly affected those astronauts. They described a sense of loneliness unlike anything experienced on Earth. The tidal lock also means that from Earth, we always see roughly the same 59% of the moon's surface. The extra 9% beyond the 50% visible at any instant comes from libration. The moon's orbit is slightly elliptical, not perfectly circular, so its orbital speed varies. Sometimes it moves faster than its rotation, letting us peek around one edge, sometimes slower, letting us peek around the opposite edge. Additionally, the Moon's rotation axis tilts slightly relative to its orbital plane, creating a north-south libration that lets us peek over the top and bottom. These librations combine to show us 59% total, though never all at once. The remaining 41% remained hidden until Soviet spacecraft photographed it in 1959, revealing a hemisphere just as ancient and battered as the near side, but distinctly different in appearance. The Apollo missions confirmed the Moon's tidal lock through seismic measurements and gravitational mapping. By placing seismometers on the surface and tracking how moonquakes propagate, scientists mapped the lunar interior. By precisely tracking spacecraft orbits and measuring how the Moon's gravity tugs on them, they determined the Moon's mass distribution. These measurements confirmed that the Moon rotates at exactly the rate needed to maintain one face toward Earth, with only tiny perturbations from other gravitational influences. The lock is stable and will persist as long as the Earth-Moon system exists in its current form. Understanding the Moon's tidal lock helps us appreciate that this configuration isn't rare or unusual. It's the expected end state for any moon orbiting close to its planet. Throughout our solar system, we find the same pattern repeated. Jupiter's 4 large moons discovered by Galileo, Io, Europa, Ganymede, and Callisto are all tidally locked. Saturn's major moons, including Titan, show the same configuration. Even small irregular moons, if they orbit close enough to their planet, eventually achieve tidal lock. The configuration is so common that finding a close orbiting moon that isn't tidally locked would be surprising and would demand explanation. Some dynamical process must be preventing the lock, perhaps perturbations from other moons or an unusually recent capture into orbit. Part 4. Mercury, the Sun's lock wanderer. While the Moon demonstrates tidal locking to a planet, Mercury shows that planets themselves can become tidally locked to their star. For decades, astronomers believed Mercury showed one face perpetually to the Sun, just as the Moon shows one face to Earth. This seemed logical given Mercury's proximity to the Sun, orbiting at only about 58 million kilometers, close enough for solar tidal forces to be substantial. Early telescopic observations showed faint surface markings that appeared fixed in position, supporting the idea of permanent lock. Astronomers imagined Mercury with one hemisphere eternally baked by the Sun and the opposite hemisphere locked in perpetual freezing night, creating the most extreme temperature gradient of any world. This understanding stood until 1965, when radio telescopes revealed the truth. By bouncing radar signals off Mercury and analyzing the Doppler shift in the returned echoes, astronomers measured Mercury's rotation rate. The results shocked the astronomical community. Mercury wasn't locked one-to-one with its orbit. Instead, it rotates exactly 3 times for every 2 orbits around the Sun, a configuration called a 3-to-2 spin orbit resonance. This means Mercury's day, the time from sunrise to sunrise at any point on its surface, doesn't equal its year as in a 1-to-1 lock. Instead, Mercury's rotation period is about 58.6 Earth days, while its orbital period is about 88 Earth days. The ratio of 88 to 58.6 equals almost exactly 1.5, or 3-to-2. This spin-orbit resonance creates bizarre solar dynamics on Mercury's surface. Imagine standing on Mercury's equator. The Sun rises slowly in the east, climbing toward the zenith over many Earth days. But as Mercury reaches certain points in its elliptical orbit, something strange happens. The orbital motion and rotation combine in such a way that the Sun appears to slow, stop, reverse direction briefly, then resume its original motion. The Sun performs a small loop in the sky before continuing its journey toward the western horizon. This retrograde motion occurs because Mercury's orbital speed varies as it swings around the Sun near perihelion, its closest approach to the Sun. Mercury's orbital angular velocity temporarily exceeds its rotational angular velocity, making the Sun appear to move backward against the background of Mercury's surface features. The 3-to-2 resonance also means that different longitudes on Mercury experience dramatically different solar heating. There are two hot poles on Mercury's equator, points that face the Sun directly when Mercury is at perihelion, receiving maximum solar heating. These points experience surface temperatures approaching 430 degrees Celsius, hot enough to melt lead. 90 degrees away in longitude are two warm poles that face the Sun when Mercury is at aphelion, its farthest point from the Sun, where solar heating is substantially less intense. This creates a striped pattern of temperature zones around Mercury's equator, a consequence of the orbital resonance. Why did Mercury settle into 3-to-2 resonance rather than 1-to-1 lock? The answer lies in Mercury's orbital eccentricity. Mercury's orbit is more elliptical than any other planet in our solar system, with an eccentricity of about 0.2. This means its distance from the Sun varies substantially, from about 46 million kilometers at perihelion to about 70 million kilometers at aphelion. This variation in distance creates variation in the strength of solar tidal forces. When Mercury is at perihelion, the Sun's tidal force is much stronger than at aphelion. This variable tidal force can capture a planet into resonances other than 1-to-1. The mathematics of orbital resonances reveals that certain ratios between rotation and orbit are more stable than others. These resonances occur where the gravitational torques average out to zero over a complete orbit, creating stable configurations. For a perfectly circular orbit, the 1-to-1 resonance is most stable, which is why most moons achieve that configuration. But for eccentric orbits like Mercury's, other resonances can be more stable. The 3-to-2 resonance represents a stable equilibrium for Mercury given its orbital parameters. Computer simulations of Mercury's rotational evolution show that starting from almost any initial rotation rate, Mercury naturally evolves toward the 3-to-2 resonance and remains there stably. Mercury's resonance demonstrates that tidal locking isn't always a simple 1-to-1 configuration. Depending on orbital properties, bodies can settle into various resonance states. Pluto's moons provide another example. Styx, Nix, Kerberos, and Hydra orbit in a complex dynamical environment dominated by Pluto and Charon. Some of these small moons tumble chaotically rather than settling into clean tidal locks, their rotational states influenced by the combined gravitational fields of both Pluto and Charon in ways that prevent stable locking. These examples remind us that while tidal locking is common, the universe offers many variations on the theme. Mercury's surface bears the scars of billions of years bathing in the Sun's radiation. The hemisphere facing the Sun during perihelion experiences extreme thermal stress as temperatures soar, then plummet during the long night. This thermal cycling causes rock to expand and contract, creating unique surface features. Mercury also lacks substantial atmosphere to distribute heat, so temperature differences between day and night are extreme. The night side can drop to -180 degrees Celsius, creating a temperature swing of over 600 degrees, the largest in the solar system. Despite the extreme dayside heat, some permanently shadowed craters near Mercury's poles contain water ice, protected from solar radiation by the crater walls and the planet's minimal axial tilt. Studying Mercury's 3-to-2 resonance has helped astronomers understand tidal evolution in other systems. When searching for planets around other stars, understanding that planets can lock into various resonances, not just 1-to-1, becomes important for predicting their climate and habitability. A planet in 3:2 resonance experiences different day-night cycles than a 1:1 locked planet, affecting temperature distribution and atmospheric dynamics. These factors influence whether the planet could support life, making Mercury's example relevant to astrobiology despite Mercury itself being far too extreme for any life we can imagine. Part 5. Tidally locked planets around other stars. Beyond our solar system, tidal locking becomes even more important and prevalent. Most planets discovered orbiting other stars, particularly those in close orbits, are very likely tidally locked to their parent stars. This isn't speculation, but a consequence of the same physics that locked our moon and influenced Mercury. When a planet orbits close to its star, stellar tidal forces become powerful enough to halt the planet's rotation relatively quickly in cosmic terms. The closer the orbit, the faster the locking occurs. For planets orbiting within their star's habitable zone, where liquid water could exist on the surface, tidal locking becomes almost certain around cool red dwarf stars. Red dwarf stars, also called M-dwarf stars, are the most common stars in our galaxy, comprising about 70% of all stars. These stars are much smaller and cooler than our Sun, with masses between about 8% and 50% of the Sun's mass. Because they're cooler, their habitable zones, the orbital distances where planets could maintain liquid water, lie much closer to the star than Earth's orbit around the Sun. A planet in the habitable zone of a red dwarf might orbit at only a few million kilometers from its star, compared to Earth's 150 million kilometer orbit around the Sun. At such close distances, tidal forces are immense, and planets lock very quickly, perhaps within a few million to a few hundred million years of formation. This creates a profound implication for the search for life beyond Earth. If most stars are red dwarfs, and most planets in red dwarf habitable zones are tidally locked, then most potentially habitable planets in the galaxy might be tidally locked worlds with permanent day and night hemispheres. This is a radically different environment than Earth. The day side would receive constant stellar illumination, never experiencing sunset or nighttime cooling. The night side would remain in perpetual darkness, never warmed by direct starlight. This stark division creates unique challenges for habitability and raises fascinating questions about what forms of life might adapt to such conditions. The day side of a tidally locked planet would face continuous stellar heating. Without rotation to distribute this heat around the planet, all the incoming stellar energy concentrates on one hemisphere. For Earth, rotation ensures that solar heating averages out. No point on the surface receives continuous illumination except near the poles during summer. But on a tidally locked planet, the substellar point, the location directly beneath the star where the star appears at the zenith, receives continuous maximum radiation. This creates extreme heating at that point. Temperatures that could be far hotter than anywhere else on the planet, potentially hot enough to boil away any water if the planet lacks mechanisms to transport heat away. The night side faces the opposite problem. With no direct stellar heating, temperatures would plummet. Heat can only reach the night side through atmospheric circulation or ocean currents if the planet has these features. Without adequate heat transport, the night side could become so cold that any atmosphere freezes out onto the surface. Gases like nitrogen and oxygen, which make up Earth's atmosphere, would condense into liquid or solid form at sufficiently low temperatures. If the entire atmosphere froze onto the night side, the planet would lose its greenhouse effect and any protection from radiation, potentially rendering it completely hostile to life. This scenario, called atmospheric collapse, worried astrobiologists when they first seriously considered tidally locked planets. If the day side is too hot and the night side is too cold, with the atmosphere freezing out on the night side, where could life exist? The answer, if it exists at all, probably lies in a narrow ring around the terminator, the boundary between day and night. The terminator would experience moderate temperatures, warmed by scattered light from the day side and cooled by proximity to the night side. Imagine standing at the terminator. The star would hang perpetually at the horizon, never rising or setting. You'd exist in eternal twilight, with gradients of temperature, light, and habitability extending in both directions. However, more sophisticated climate models suggest that atmospheric collapse might not be inevitable. If a planet has a sufficiently thick atmosphere, atmospheric circulation could transport heat from the day side to the night side effectively enough to prevent freezing. On Earth, atmospheric circulation moves heat from the equator to the poles, moderating temperatures at all latitudes. On a tidally locked planet, circulation would move heat from the substellar point to the antistellar point, the location on the night side directly opposite the star. Strong winds would blow from the hot day side to the cold night side, carrying heat energy with them. If this heat transport is efficient enough, the night side might remain warm enough to prevent atmospheric collapse. Ocean currents could also help. If a tidally locked planet has liquid water oceans, these could circulate between the day and night sides, absorbing heat from the day side and releasing it on the night side. Earth's ocean currents transport enormous amounts of heat. The Gulf Stream alone carries more heat energy than all human power generation combined. On a tidally locked planet, ocean circulation could similarly moderate temperatures, potentially keeping both hemispheres habitable. The ocean might even circulate in a simple pattern, warming on the day side, rising and flowing toward the night side, cooling and sinking there, then returning to the day side along the bottom. This giant conveyor belt would mix heat around the planet. Recent three-dimensional climate simulations of tidally locked planets around red dwarf stars suggest that many such worlds could indeed maintain stable atmospheres and surface conditions potentially suitable for life. The key factors are atmospheric mass and composition. A planet with a thick atmosphere rich in greenhouse gases like carbon dioxide could trap enough heat to prevent night-side freezing. The strong atmospheric circulation patterns that develop, driven by the day-night temperature gradient, help distribute heat effectively. Some models even suggest that tidally locked planets might have larger habitable surface areas than rotating planets like Earth, with the Terminator region offering the most temperate climate and both the deep day side and deep night side remaining potentially habitable under the right atmospheric conditions. Part 6. The Terminator Zone. The Terminator, that boundary between eternal day and eternal night on a tidally locked world, represents one of the universe's most intriguing potential habitats. On Earth, the Terminator is the moving shadow line we know as dawn or dusk, sweeping around the planet as it rotates. But on a tidally locked planet, the Terminator is fixed in space, a permanent twilight zone encircling the planet. This region would experience conditions unlike anywhere on Earth, with the star hanging perpetually at the horizon, casting long shadows and creating a band of moderate temperatures between the blazing day side and frozen night side. Standing at the Terminator would offer a surreal experience. Looking toward the day side, you'd see the sky gradually brightening, though the star itself would remain hidden below the nearby horizon. The landscape would glow with scattered light, perhaps tinted red or orange if the star is a red dwarf, bathing everything in perpetual sunset colors. Looking toward the night side, darkness would deepen, with stars becoming visible overhead and the temperature dropping noticeably. The gradient would be steep. Walking a few kilometers toward either hemisphere would bring you into markedly different conditions. The Terminator itself would exist as a narrow band where conditions are just right, a Goldilocks zone on a planet already located in its star's Goldilocks zone. The width of this habitable terminator band would depend on several factors. Atmospheric circulation plays a crucial role. Strong winds would tend to widen the band by mixing air from both sides, preventing sharp temperature transitions. A thick atmosphere would scatter light further into the night side and transport heat more efficiently, again widening the habitable region. The planet's geology and surface composition would matter too. Darker surfaces absorb more light and heat up more than reflective surfaces. A planet with extensive ice or snow on the night side, reflecting light back into space, would have a sharper transition than one with dark rock or soil that absorbs available light efficiently. Imagine the ecosystems that might develop in the Terminator Zone. Plants, if they exist, would adapt to constant twilight conditions. Unlike Earth plants that experience day-night cycles, these organisms would photosynthesize continuously under unchanging light levels. They might evolve pigments optimized for the particular wavelengths emitted by their star, likely red or infrared for a red dwarf star. Without day-night cycles, circadian rhythms might never evolve. Life wouldn't operate on daily cycles but might instead respond to other environmental variations, perhaps weather patterns driven by atmospheric circulation or seasonal changes if the planet's orbit is eccentric. Animals in the Terminator Zone might navigate using the star's position as a constant reference point. On Earth, many species use the sun for navigation, compensating for its movement across the sky. On a tidally locked world, the star's fixed position would provide an unwavering compass. A creature could navigate simply by maintaining a specific angle relative to the star's position on the horizon. Migration patterns, if they exist, might run along lines of latitude circling the planet parallel to the Terminator, staying within preferred temperature ranges, rather than the pole to equator migrations common on Earth. The Terminator Zone might also feature unique weather patterns. The temperature gradient between day and night sides would drive persistent winds. Air heated on the day side would rise and flow toward the night side at high altitude, while cool air from the night side would flow toward the day side at low altitude, creating a global circulation cell. This circulation would be much simpler than Earth's complex weather systems, which arise partly from our planet's rotation via the Coriolis effect. On a slowly rotating or tidally locked planet, the Coriolis effect would be weak or absent, allowing more direct circulation patterns. The Terminator might experience persistent cloud cover where warm moist air from the day side rises and cools, condensing moisture into clouds or precipitation. Some models suggest that tidally locked planets could develop a permanent cloud shield over the substellar point. As the hottest air rises most strongly there, moisture would rise with it, cooling and forming thick clouds. These clouds would reflect some incoming starlight back to space, helping to moderate the temperature and prevent runaway heating. The cloud shield would be self-regulating. If the surface got too hot, more moisture would evaporate, creating more clouds, reflecting more light, cooling the surface. This negative feedback could stabilize temperatures in what might otherwise become an uninhabitable hotspot. The Terminator, benefiting from this moderated climate on the day side and receiving some scattered light and heat, could become even more favorable for life. Water might behave strangely on a tidally locked world. If the night side is cold enough, any water there might freeze into massive ice sheets. These ice sheets could grow over time as atmospheric moisture migrates to the night side and precipitates out. Eventually, this could trap most of the planet's water in night side ice, leaving the day side dry. However, if the planet has geological activity like volcanic eruptions, these could periodically release water vapor back into the atmosphere. Alternatively, if enough heat reaches the night side through atmospheric circulation, a balance might establish itself where ice at the coldest regions coexists with liquid water in warmer areas. perhaps creating a planet-spanning ocean that freezes on the night side and remains liquid toward the terminator and on the day side. The prospects for life in the terminator zone depend heavily on liquid water availability. If water can remain liquid anywhere in this region, and if the planet has the necessary chemical building blocks like carbon, nitrogen, and phosphorus, then life might arise. The constant conditions could favor complexity. On Earth, organisms must cope with daily and seasonal variations, investing energy and adaptations to handle these changes. On a tidally locked world, the unchanging environment might allow life to specialize more narrowly, potentially leading to different evolutionary paths. Without the stress of environmental cycling, perhaps complexity could arise faster, or perhaps the lack of environmental pressure would slow evolution. We simply don't know, and that uncertainty makes these worlds fascinating targets for future study. Part 7. Worlds Beyond the Terminator. While the Terminator Zone might offer the most obviously habitable conditions, the deep day side and deep night side of tidally locked planets present their own intriguing possibilities. These are the extreme regions, places where the star hangs high in the sky perpetually or where darkness never lifts. At first glance, these seem uninhabitable, too hot or too cold for life as we know it. Yet nature has surprised us before, and organisms on Earth thrive in environments once thought impossible for life. Exploring what might exist beyond the Terminator stretches our imagination and our understanding of life's possibilities. The substellar point, where the star appears directly overhead, would be the hottest place on a tidally locked planet. All the star's radiation focuses here, creating intense heating. On a planet without thick atmosphere, temperatures could exceed what any known organism can tolerate. Water would boil away, organic molecules would break down, and the surface might resemble a sun-baked desert more extreme than anything on Earth. But with a substantial atmosphere, conditions might moderate somewhat. High-altitude clouds could reflect much of the radiation before it reaches the surface. Strong convection currents would carry hot air upward and away, replaced by cooler air flowing in from other regions. The surface temperature at the substellar point might still be hot, perhaps comparable to Earth's hottest deserts, but not necessarily lethal. Life on Earth provides examples of extreme heat tolerance. Thermophilic bacteria live in hot springs at temperatures above 70 degrees Celsius. Some archaea survive above 100 degrees Celsius in deep-sea hydrothermal vents, where pressure keeps water liquid above its normal boiling point. While no known organism thrives at 200 or 300 degrees Celsius, these examples show that life can adapt to heat far beyond what humans tolerate. On a tidally locked planet's day side, if atmospheric conditions kept surface temperatures below, say, 150 degrees Celsius, and if liquid water existed in some form, perhaps underground or in shaded crevices, microbial life might find a way. The night side presents different challenges. In perpetual darkness and cold, temperatures would plunge. Without sunlight, photosynthesis becomes impossible, eliminating the foundation of most ecosystems on Earth. Any atmosphere thin enough to allow the night side to freeze would collapse there, creating a frozen wasteland. But if the atmosphere is thick enough to transport heat from the day side, the night side might remain merely cold rather than frozen. Think of polar regions on Earth. Even during polar winter, when the sun doesn't rise for months, temperatures rarely drop below -50 or 60 degrees Celsius because atmospheric circulation brings heat from lower latitudes. A tidally locked planet's night side might experience similar moderation. In such conditions, life would need to operate without sunlight. On Earth, many ecosystems function without photosynthesis. Deep-sea hydrothermal vent communities survive on chemosynthesis, where bacteria extract energy from chemical reactions involving minerals dissolved in hot vent fluids. These communities include bacteria, tube worms, crabs, and fish, all living in complete darkness. Similar chemosynthetic ecosystems exist in caves and the deep subsurface of the ocean floor, and even within rocks kilometers underground. If a tidally locked planet's night side has geological activity providing chemical energy, perhaps through volcanic vents or radioactive decay heating groundwater, chemosynthetic life could potentially establish itself. Another energy source might come from the planet's interior. All planets generate internal heat through radioactive decay of elements like uranium, thorium, and potassium in their cores and mantles. Earth loses this heat gradually through volcanic activity and geothermal vents. On a tidally locked planet, particularly one experiencing tidal flexing from an eccentric orbit or from the gravitational influence of other planets or moons, internal heating could be substantial. This heat could warm the night side from below, melting subsurface ice into liquid water and providing energy for life. Organisms could cluster around geothermal heat sources, creating oases of warmth in an otherwise frozen landscape. The permanent darkness of the night side might even offer advantages for certain types of life. Radiation from space, including ultraviolet light and cosmic rays, can damage DNA and other biological molecules. On Earth, the ozone layer shields surface life from much of this radiation, and organisms have evolved various repair mechanisms. But the day side of a tidally locked planet around a red dwarf star would receive continuous radiation exposure. Red dwarfs are prone to stellar flares, sudden brightenings that release intense ultraviolet and X-ray radiation. These flares could make the day side surface hazardous for life. The night side, shielded from stellar radiation, might actually be safer. Life there would face cold and darkness, but not radiation, a different set of challenges requiring different adaptations. One intriguing possibility involves underground ecosystems. On Earth, we've discovered extensive microbial communities living in rock formations kilometers beneath the surface. These organisms survive on chemical energy from rock-water interactions and reproduce extremely slowly, sometimes over timescales of thousands of years. A tidally locked planet could host similar subsurface biospheres, divorced from surface conditions entirely. The day-night divide would become irrelevant. Life would extract energy from the planet's geology, with liquid water moving through rock fractures, dissolving minerals, and providing nutrients to microbes. These deep biospheres might exist on both hemispheres, never aware of the star overhead or the frozen ice above. The possibility of life on tidally locked planets remains speculative, but the physics that creates these worlds is well understood. As we discover more planets around other stars and develop better instruments to study them, we'll gain insights into how common these configurations are and what conditions actually exist on their surfaces. Future telescopes might detect atmospheric signatures indicating biological activity, such as oxygen or methane in combinations that suggest life. If we detect such signatures on a tidally locked planet, we'll face the exciting challenge of understanding how life adapted to permanent day and night, expanding our conception of where and how life can exist. Part 8. Pluto and Charon, the double lock. Among all the tidally locked bodies in our solar system, Pluto and its largest moon Charon exhibit the most elegant and complete form of tidal locking. They're not just individually locked, they're mutually locked, each showing only one face to the other for eternity. This mutual configuration represents the final stable state of tidal evolution, where both bodies have synchronized perfectly. When you stand on Pluto's Charon-facing hemisphere, Charon hangs motionless in the sky, always in the same position, never rising or setting. When you stand on Pluto's opposite hemisphere, Charon remains forever below the horizon, invisible. The same holds true from Charon. Pluto appears fixed in Charon's sky, a beautiful blue-gray sphere that never moves. This mutual lock resulted from the unusual mass ratio between Pluto and Charon. Charon is quite large relative to Pluto, about 1/8 Pluto's mass and just over half Pluto's diameter. This makes the Pluto-Charon system more like a double planet than a traditional planet-moon pair. Their center of mass, the barycenter around which both bodies orbit, lies outside Pluto's surface, in space between the two bodies. Both Pluto and Charon orbit this common point. Because Charon's mass is substantial compared to Pluto's, Charon exerted significant tidal forces on Pluto even as Pluto tidally influenced Charon. Over time, both bodies slowed their rotations until they became synchronized with their mutual orbit. The orbital period of the Pluto-Charon system is 6.39 Earth days. This is also the rotation period of both Pluto and Charon. Every 6.39 days, both bodies complete one rotation on their axes and one orbit around their common center of mass, maintaining their locked orientations. This triple synchronization creates a beautifully stable dynamical system. If you could watch from far above the orbital plane, you'd see Pluto and Charon orbiting their barycenter like two dancers holding hands and spinning together, each always facing the other, never breaking eye contact. The timescale for achieving this mutual lock was relatively short compared to the age of the solar system. Calculations suggest that Pluto and Charon locked within a few 100 million years of Charon's formation. The origin of Charon remains somewhat uncertain, but the leading theory proposes a giant impact, similar to how Earth's moon formed. A large object struck Pluto early in solar system history, ejecting debris that coalesced into Charon. If this scenario is correct, Charon started much closer to Pluto than today and receded over time as tidal interactions transferred rotational energy to orbital energy. During this recession, both bodies evolved toward tidal lock, with Pluto locking first because Charon's tidal influence on Pluto was stronger than Pluto's influence on Charon due to Charon's closer proximity initially. Walking on Pluto's Charon-facing hemisphere would offer spectacular views. Charon would appear about 8 times larger in angular diameter than our moon appears from Earth, spanning roughly 4 degrees of sky. You'd see surface details clearly, including Charon's distinctive red polar cap, created by frozen hydrocarbons deposited from Pluto's escaping atmosphere. Charon would go through phases as Pluto orbits the Sun. When Pluto is positioned so the Sun illuminates Charon from your perspective, you'd see full Charon. A quarter of Pluto's orbital period later, 90 Pluto years equals about 228 Earth years, you'd see half Charon illuminated. The phases would progress slowly, completing a full cycle every Pluto year, but Charon's position in the sky would never change. The mutual lock creates unique consequences for Pluto's small outer moons, Styx, Nix, Kerberos, and Hydra. These tiny bodies orbit beyond Charon in the combined gravitational field of the Pluto-Charon binary system. The gravitational field isn't centered on a single point but distributed between Pluto and Charon, creating a complex environment. Some of these moons exhibit chaotic rotation, their spin axes tumbling unpredictably due to the complicated torques from both Pluto and Charon. This makes them among the few bodies in our solar system that haven't settled into stable tidal locks, despite having been in their orbits for billions of years. The chaotic region where tidal torques from two comparable bodies interfere prevents clean locking. The mutual lock also affects Pluto's geology in subtle ways. Tidal forces between Pluto and Charon generate some heat through friction, though much less than in more extreme cases like Io and Jupiter. This heating may contribute to maintaining Pluto's tenuous nitrogen atmosphere and driving some geological activity. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a geologically active world with smooth plains suggesting recent resurfacing, towering water ice mountains, and flowing nitrogen glaciers. Some of this activity might be powered by residual heat from radioactive decay and from past tidal heating when the system was evolving toward its current locked state. Mutual tidal locking isn't unique to Pluto and Charon. Similar configurations might exist around other stars, particularly in binary star systems where two stars orbit each other closely. If those stars are similar in mass, they could become mutually tidally locked, always showing the same faces to each other as they orbit their common center of mass. Binary stars that orbit close enough often exhibit synchronized rotation, though proving mutual lock requires careful observation of surface features, which is challenging for distant stars. In our solar system, Pluto and Charon remain the only confirmed example of mutual tidal lock, making them a precious laboratory for understanding this dynamical state. Part 9. The Galilean Moons and Tidal Resonances. Jupiter's four largest moons, discovered by Galileo Galilei in 1610, showcase tidal locking and more complex tidal interactions. Io, Europa, Ganymede, and Callisto all maintain one face toward Jupiter, just as our moon does toward Earth. But the inner three of these moons, Io, Europa, and Ganymede, participate in something more intricate, a phenomenon called orbital resonance. For every 4 orbits Io completes around Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. This 4:2:1 ratio creates a stable configuration where the gravitational influences of these moons reinforce each other rather than randomizing their orbits. This resonance arose through tidal evolution over millions of years. As Jupiter's tidal forces gradually changed the moon's orbits, they fell into this locked pattern where the orbital periods maintain simple integer ratios. The resonance is self-reinforcing. If one moon drifts slightly off schedule, the gravitational tugs from the other moons act to pull it back into sync. This creates long-term stability. The resonance has persisted for perhaps billions of years and will continue far into the future. Similar resonances appear throughout the solar system, their signatures of tidal forces sculpting orbital architectures into mathematically elegant patterns. For the moons themselves, the resonance creates important consequences. Consider Io, the innermost of the 3 resonant moons. Io's orbit would normally be nearly circular if it orbited Jupiter alone. Tidal forces would have circularized it long ago. But Europa and Ganymede, locked in resonance with Io, periodically tug on it, preventing complete circularization. These tugs maintain a slight eccentricity in Io's orbit, meaning Io's distance from Jupiter varies slightly during each orbit. As Io swings closer to Jupiter, tidal forces strengthen, stretching Io into a more elongated shape. As Io swings farther away, tidal forces weaken, and Io relaxes toward a more spherical shape. This rhythmic squeezing and releasing happens every 42.5 hours, Io's orbital period. The tidal flexing pumps enormous energy into Io's interior. Rock doesn't compress and expand elastically like rubber, it experiences friction and converts the mechanical flexing into heat. The heat is so intense that Io's interior remains partially molten despite Io being a small moon that would have otherwise cooled and solidified billions of years ago. This internal heat drives Io's spectacular volcanism. Hundreds of volcanoes dot Io's surface, erupting continuously. Some erupt silicate lava like Earth's volcanoes, while others erupt sulfur and sulfur dioxide. The volcanic activity resurfaces Io so rapidly that impact craters, common on other moons, are virtually absent. Lava flows bury any craters within thousands of years, making Io the youngest surface in the solar system in terms of average age. Europa, the next moon outward, experiences less intense tidal heating than Io, but enough to maintain a subsurface ocean beneath its icy shell. Europa's surface consists of water ice, crisscrossed with cracks and ridges suggesting the ice floats on liquid water below. The orbital resonance keeps Europa's orbit slightly eccentric, creating tidal flexing similar to Io's but less extreme. This flexing generates heat that melts ice in Europa's interior, maintaining a liquid water ocean perhaps 100 kilometers deep beneath a surface ice shell perhaps 10 to 30 kilometers thick. This ocean is one of the most promising places to search for life in our solar system. It contains more liquid water than all of Earth's oceans combined and has existed for potentially billions of years, providing time for life to arise. Ganymede, the largest moon in the solar system, bigger than the planet Mercury, also participates in the resonance. Ganymede's orbit is more circular than Europa's or Io's because Ganymede is farther from Jupiter where tidal forces are weaker. But the resonance still affects Ganymede, maintaining slight orbital eccentricity that generates some tidal heating. Ganymede may also have a subsurface ocean, though deeper and less accessible than Europa's. Observations from spacecraft reveal magnetic field signatures consistent with a salty ocean conducting electricity beneath Ganymede's icy and rocky surface layers. This ocean probably exists because of residual heat from Ganymede's formation combined with modest tidal heating and radioactive decay in Ganymede's rocky core. Callisto, the outermost Galilean moon, doesn't participate in the resonance. Its orbit evolved independently, and it settled into a nearly circular orbit without the gravitational reinforcement from the other moons. Without significant tidal heating, Callisto remained geologically quiet. Its surface is heavily cratered, ancient, and stable, contrasting sharply with Io's dynamic volcanism. Callisto might also have a subsurface ocean, detected through magnetic field measurements, but this ocean would be maintained purely by residual formation heat and radioactive decay, not tidal heating. Callisto serves as a control case, showing what a Galilean moon looks like without resonant tidal interactions. All 4 Galilean moons are tidally locked to Jupiter with 1-to-1 spin-orbit synchronization. From any point on Io, Europa, Ganymede, or Callisto, Jupiter hangs fixed in the sky. For observers on the Jupiter-facing hemisphere of any moon, Jupiter would dominate the sky, appearing enormous. Jupiter's angular diameter is seen from Io spans about 20 degrees, roughly 40 times the size of our moon is seen from Earth. Jupiter would go through phases as the sun illuminates different portions from the moon's perspective, but would never rise or set. This locked configuration ensures that tidal bulges on each moon remain stationary relative to Jupiter, but the orbital resonance makes those bulges change size rhythmically, creating the flexing that heats the interiors. Part 10: Saturn's Moons and Tidal Mysteries. Saturn's moon system rivals Jupiter's in complexity and showcases additional facets of tidal locking and tidal evolution. Most of Saturn's major moons are tidally locked to Saturn, including Mimas, Enceladus, Tethys, Dione, Rhea, Titan, and Iapetus. Each maintains one face towards Saturn throughout its orbit, a testament to the power of Saturn's tidal forces. But among these moons, Enceladus stands out as one of the solar system's most intriguing bodies, a small icy moon exhibiting geological activity driven by tidal heating in ways we're still working to fully understand. Enceladus is tiny, only about 500 kilometers in diameter, roughly 1/7 the diameter of our moon. A body this small should have frozen solid billions of years ago, its internal heat radiated away into space. Yet when NASA's Cassini spacecraft flew close to Enceladus, it discovered enormous plumes of water vapor, ice particles, and organic molecules erupting from cracks near the South Pole. These cracks, nicknamed tiger stripes for their appearance, are warmer than surrounding terrain. The plumes shoot hundreds of kilometers above the surface, feeding Saturn's E-ring with fresh ice particles. The discovery shocked scientists because it revealed ongoing geological activity on a body that by all conventional reasoning should be geologically dead. Tidal heating provides the most plausible explanation for Enceladus's activity. Enceladus orbits Saturn with a slight orbital eccentricity, meaning its distance from Saturn varies during each orbit. This eccentricity likely results from orbital resonances with other moons, particularly Dione, which orbits with exactly twice Enceladus's orbital period, creating a 2-to-1 resonance. As Enceladus swings closer to and farther from Saturn, tidal forces flex the moon, generating friction and heat. The heat concentrates in the South Polar region for reasons still debated, possibly related to the ice shell's thickness or past impacts that thinned the ice there. This localized heating melts subsurface ice, creating a liquid water reservoir or ocean beneath the South Pole. Pressure from the ocean forces water up through the cracks, where it erupts as geysers. The geysers provide a direct sample of Enceladus's subsurface ocean. Cassini flew through the plumes, analyzing their composition with onboard instruments. The measurements revealed water vapor, salt, silica particles, and complex organic molecules, including some relevant to biochemistry. The salt and silica indicate the water interacts with rock, likely at the bottom of the ocean where water contacts Enceladus's rocky core. Such water-rock interactions could provide chemical energy for life, similar to Earth's hydrothermal vents. The organic molecules suggest chemical complexity, though whether they're biological or abiological remains unknown. Enceladus's ocean has become another top target in the search for extraterrestrial life. Titan, Saturn's largest moon, presents a different tidal story. Titan is tidally locked to Saturn and possesses a thick nitrogen atmosphere, the only moon in the solar system with a substantial atmosphere. Beneath Titan's orange smoggy clouds lies a surface with lakes and seas of liquid methane and ethane, especially near the poles. Beneath the surface, evidence suggests a subsurface water ocean exists, perhaps 100 kilometers down. This ocean isn't directly accessible like Enceladus's because it's buried under a thick icy shell and possibly layers of high-pressure ice. Yet its presence is inferred from measurements of Titan's shape and how Titan responds to Saturn's tides. Titan's response to tidal forces reveals its internal structure. As Titan orbits Saturn, Saturn's gravity raises tidal bulges in Titan. If Titan were completely solid, these bulges would be small and rigid. But measurements show Titan deforms more than a solid body would, suggesting it has a liquid layer inside that allows the surface to shift. The size of the tidal deformation indicates that this liquid layer exists at a specific depth, consistent with a global ocean beneath the ice shell. The ocean probably persists due to a combination of ammonia acting as antifreeze, lowering water's freezing point, and residual heat from radioactive decay in Titan's core, supplemented by modest tidal heating. Iapetus, one of Saturn's outer moons, displays a bizarre two-tone coloration. One hemisphere is bright icy white while the other is dark reddish brown. Iapetus is tidally locked to Saturn, and the dark material concentrates on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn. The origin of this pattern involves tidal locking indirectly. The leading hemisphere sweeps up dark dust particles orbiting Saturn, possibly from the disintegration of outer small moons. Over millions of years, this dust accumulates on the leading face. As the dark material absorbs more sunlight than surrounding ice, it warms slightly, causing some ice to sublimate. The sublimated ice refreezes on the colder, bright trailing hemisphere, creating a feedback loop that sharpens the contrast. Tidal lock ensures that the same hemisphere always leads, maintaining the pattern. Mimas, another of Saturn's moons, orbits closer to Saturn than Enceladus yet shows no signs of geological activity despite experiencing comparable tidal forces. Its surface is ancient and heavily cratered, dominated by a giant impact crater named Herschel that spans 1/3 of Mimas's diameter. The lack of activity on Mimas compared to Enceladus puzzles scientists. Both moons are similar in size and experience similar tidal forces, yet one is geologically dead while the other erupts with plumes. The difference might lie in internal structure or past orbital evolution. Perhaps Mimas never developed the orbital eccentricity that Enceladus has, or perhaps differences in ice shell thickness or composition prevent tidal heating from generating enough warmth to melt Mimas's interior. Studying Saturn's moons reveals that tidal locking is only the beginning of the story. Once locked, moons continue to evolve through tidal interactions, orbital resonances with other moons, and internal processes. Predicting which moons become geologically active and which remain inert requires understanding not just current tidal forces but the entire orbital history and internal composition. Each moon provides clues, and together they paint a picture of tidal evolution as a nuanced process producing diverse outcomes even among superficially similar bodies. Part 11: Exoplanets and Future Observations. The discovery of thousands of planets orbiting other stars has revolutionized our understanding of planetary systems and tidal locking. Many of these planets orbit much closer to their stars than Mercury orbits our Sun, experiencing intense stellar radiation and strong tidal forces. These close orbiting planets, often called hot Jupiters when they're gas giants or hot Earths when they're rocky, are very likely tidally locked. Understanding tidal locking in these systems helps astronomers predict their climates, atmospheric dynamics, and potential habitability. Hot Jupiters were among the first types of planets discovered around other stars because they're relatively easy to detect. Their large masses create measurable wobbles in their parent stars through gravitational tugging, and their close orbits mean these wobbles happen frequently, making detection straightforward. Planets like 51 Pegasi b, the first confirmed planet around a Sun-like star, orbit at distances of only a few million kilometers from their stars with orbital periods measured in Earth days. At such proximity, tidal forces lock these planets very quickly, probably within a few million years. These gas giants therefore present one face continuously to their stars. The climate on a tidally locked hot Jupiter would be extreme and alien. The day side receives continuous intense stellar radiation, heating the atmosphere to thousands of degrees. Gases like sodium and potassium exist in vapor form. The night side, receiving no direct stellar light, cools somewhat but remains hot due to atmospheric circulation. Strong winds, potentially reaching thousands of kilometers per hour, blow from the day side to the night side, driven by the temperature gradient. These winds transport heat, preventing the night side from cooling as much as it otherwise would. Observations using the Hubble and Spitzer space telescopes detected these temperature differences by measuring how much infrared radiation the planets emit at different orbital phases. Rocky planets in close orbits face similar tidal locking. Planets discovered in the habitable zones of red dwarf stars, where temperatures allow liquid water, are prime candidates for detailed study. Stars like TRAPPIST-1, a cool red dwarf 40 light-years away, hosts 7 known planets, several of which orbit in or near the habitable zone. These planets orbit extremely close to their star because TRAPPIST-1 is so dim that its habitable zone lies only a few million kilometers away. At these distances, tidal locking is essentially guaranteed. The planets almost certainly show one face to their star, creating permanent day and night hemispheres. Future telescopes will characterize these planets' atmospheres and surface conditions. The James Webb Space Telescope, launched in 2021, has already begun studying planetary atmospheres by observing how starlight filters through the atmosphere when the planet passes in front of its star. This technique, called transmission spectroscopy, reveals which gases exist in the atmosphere by identifying their absorption signatures. For tidally locked planets, scientists hope to map temperature differences between day and night sides by observing the planet throughout its orbit and measuring how much heat it radiates at different phases. If the night side is very cold, the planet will radiate less heat when the night side faces us. If atmospheric circulation effectively transports heat, the day-night temperature difference will be smaller. Another goal involves detecting potential biosignatures, chemical signs that might indicate life. Oxygen in an atmosphere could suggest photosynthetic life, though geological processes can also produce oxygen. Methane combined with oxygen is more intriguing because methane and oxygen react together, so their simultaneous presence requires continuous replenishment, potentially from biological sources. On a tidally locked planet, life might produce different biosignatures depending on where it exists. If life concentrates in the terminator zone, atmospheric patterns might show chemical gradients aligned with the day-night boundary. Detecting such patterns would require detailed mapping of atmospheric composition across the planet's surface, a challenging task but potentially within reach of future observatories. Ground-based telescopes are also contributing. Extremely large telescopes under construction, like the European Extremely Large Telescope with a 39-meter primary mirror, will directly image some nearby planets and study their atmospheres through spectroscopy. For tidally locked planets, this might reveal surface features if the planet has continents, oceans, or ice caps. A planet with an ocean on the day side and ice on the night side might show distinct spectral signatures in different regions. Mapping these features would provide insights into how heat and water distribute themselves on tidally locked worlds. The search for habitable tidally locked planets also raises questions about the definition of habitability. Traditional definitions focus on the presence of liquid water, but tidal locking creates conditions so different from Earth that we might need to expand our thinking. A planet with liquid water only in a narrow terminator band might still be habitable, even if most of its surface is frozen or baked. Life might adapt to the unchanging twilight, creating ecosystems unlike any on Earth. Alternatively, subsurface oceans heated by tidal or geothermal energy could provide habitable environments regardless of surface conditions. Enceladus and Europa teach us that oceans beneath ice can persist for billions of years, potentially hosting life divorced from surface sunlight. As we discover more planets and characterize their properties, tidal locking emerges as a fundamental organizing principle for planetary climates and habitability. It's not an exotic edge case, but potentially the most common configuration for planets in habitable zones around the galaxy's most common stars. Understanding tidal locking, therefore, becomes central to astrobiology and the search for life beyond Earth. Every tidally locked planet we study teaches us about the diversity of planetary environments and expands the range of conditions we consider potentially habitable. Part 12: The Long-Term Evolution of Tidally Locked Systems. Tidal locking isn't a final static state, but part of an ongoing evolution that continues over billions of years. Even after a moon or planet becomes tidally locked, tidal forces keep working, gradually changing orbital parameters and potentially unlocking bodies under certain circumstances. The Earth-Moon system provides a clear example. The Moon is tidally locked to Earth and has been for billions of years, yet tidal interactions haven't stopped. The Moon continues to recede from Earth at about 3.8 centimeters per year, a slow but steady drift that will continue for billions of years into the future. This recession happens because Earth itself isn't tidally locked to the Moon. Earth rotates much faster than the Moon orbits, completing one rotation every 24 hours while the Moon orbits every 27.3 days. As Earth rotates, it drags tidal bulges in its oceans raised by the Moon's gravity. These bulges don't align perfectly with the Earth-Moon line because friction in shallow seas and around continental margins delays the bulges slightly. The offset bulges create a gravitational torque that pulls on the Moon, accelerating it in its orbit. As the Moon's orbital speed increases, it spirals outward to conserve energy and angular momentum. Meanwhile, the torque on Earth acts as a brake, slowing Earth's rotation and lengthening the day. This process has been ongoing since the Moon formed about 4.5 billion years ago. Early in Earth's history, the Moon orbited much closer, perhaps only 20,000 kilometers away compared to today's 384,000 kilometers. At that proximity, Earth's day was only about 5 hours long. The Moon orbited in perhaps only a few hours and appeared enormous in the sky. Tidal forces raised massive tides in Earth's early oceans, and the Moon receded much faster than today. Over time, as the Moon moved farther away and Earth's rotation slowed, the recession rate decreased. Eventually, in about 50 billion years, if the Sun doesn't expand and destroy both bodies first, Earth will become tidally locked to the Moon. At that point, both Earth's rotation period and the Moon's orbital period will match at about 47 current days, and the Moon will hang motionless in Earth's sky just as Earth hangs motionless in the lunar sky today. Other systems show similar long-term evolution. Mars' moon Phobos is spiraling inward rather than outward because Phobos orbits faster than Mars rotates. Mars rotates once every 24.6 hours, while Phobos orbits every 7.6 hours. The tidal bulges Mars raises on Phobos, and Phobos raises on Mars, interact such that Phobos loses orbital energy and descends toward Mars. In about 50 million years, Phobos will either crash into Mars or break apart under tidal stress when it crosses Mars' Roche limit, the distance where tidal forces exceed the Moon's self-gravity. The debris might form a temporary ring around Mars before gradually falling to the surface. Tidal evolution can also unlock bodies under special circumstances. If a planet's orbit around its star becomes significantly eccentric due to gravitational interactions with other planets, the tidal forces the planet experiences will vary in strength throughout its orbit. This variable forcing can pump energy into the planet's rotation, potentially breaking a tidal lock. The planet might then enter a spin-orbit resonance like Mercury's 3-2 configuration rather than 1-1 lock. If the orbit later circularizes, the planet might re-lock into 1-1. This type of complex evolution probably occurred in many planetary systems as planets migrated and interacted gravitationally during the chaotic early phases of system formation. Binary star systems provide another context for tidal evolution. Two stars orbiting each other closely enough will tidally interact, potentially locking their rotations to their orbital period. Many close binary stars show synchronized rotation, both stars rotating once per orbit and maintaining the same face toward each other. As the stars age, mass transfer between them can change the orbital dynamics. If one star swells into a red giant and spills material onto its companion, the added mass and angular momentum alter the orbit, potentially breaking the tidal lock temporarily. The system then evolves toward a new locked configuration appropriate for the changed parameters. Tidal heating over billions of years affects the internal structure of moons and planets. Io's continuous volcanic resurfacing means Io's interior never fully solidifies. The constant heat output from tidal friction keeps rock molten. Over billions of years, this has likely differentiated Io's interior, with heavier elements sinking toward the core and lighter materials rising toward the surface, similar to how Earth's interior differentiated early in our planet's history. For Europa and Enceladus, tidal heating maintains subsurface oceans that might have existed for most of solar system history. These oceans provide stable environments where, if life arose, it could evolve for billions of years. The long-term fate of tidally locked systems depends on external factors too. Stellar evolution plays a major role. As stars age, they brighten and eventually expand. When our sun becomes a red giant in about 5 billion years, it will swell to perhaps 100 times its current radius, possibly engulfing Mercury and Venus and certainly baking Earth. The increased stellar radiation will heat planets and moons, changing their surface conditions. Tidally locked planets around red dwarf stars face different stellar evolution. Red dwarfs burn their nuclear fuel extremely slowly and can remain stable for trillions of years, far longer than the current age of the universe. Tidally locked planets around red dwarfs could maintain stable conditions for extraordinarily long periods, offering vast timescales for life to evolve and develop complexity. Part 13. Tidal forces in extreme environments. Beyond the familiar contexts of moons and planets, tidal forces operate in extreme environments throughout the universe, creating effects far more dramatic than anything in our solar system. Near neutron stars and black holes, tidal forces become so intense they can tear apart ordinary matter, creating streams of disrupted material spiraling into the compact object. Understanding these extreme tides connects the gentle locking of moons to the violent dynamics of the most energetic phenomena in the cosmos. Neutron stars are the collapsed cores of massive stars that exploded as supernovas. They pack about 1.4 times the sun's mass into a sphere only about 20 kilometers in diameter, creating densities so high that atomic nuclei touch. The gravitational field near a neutron star is immense, and the tidal forces are correspondingly extreme. If you fell toward a neutron star feet first, the gravitational pull on your feet would far exceed the pull on your head, even over the short distance of your body height. This differential stretching, called spaghettification, would elongate you into a thin stream of atoms long before you reached the surface. For larger objects, tidal disruption can occur at greater distances. A moon or planet orbiting too close to a neutron star would be ripped apart by tides. The inner side of the body experiences stronger gravity than the outer side, and if this differential exceeds the body's self-gravity holding it together, the body disintegrates into a debris cloud. The critical distance where this occurs is called the Roche limit, named after the French astronomer Édouard Roche, who calculated it in the 1800s. For a moon orbiting a planet, the Roche limit typically lies at about 2.5 times the planet's radius, though the exact value depends on the densities of both bodies. Saturn's rings likely formed from moons or comets that wandered inside Saturn's Roche limit and were torn apart by tides. The ring particles, ranging from dust grains to house-sized chunks of ice, all orbit within the Roche limit where tidal forces prevent them from coalescing into a moon. If you tried to collect ring particles together into a larger body while inside the Roche limit, tidal forces would pull your creation apart faster than gravity could hold it together. This same process creates rings around all 4 gas giant planets in our solar system and contributes to the disintegration of comets that pass too close to Jupiter or the Sun. Black holes generate even more extreme tidal forces. A black hole's event horizon, the boundary beyond which nothing can escape, is surrounded by a region where tidal forces are lethal. For a stellar mass black hole, perhaps 10 times the Sun's mass, the tidal forces become deadly well before you reach the event horizon. You'd be spaghettified and torn into a stream of subatomic particles. Interestingly, for supermassive black holes millions or billions of times the Sun's mass, the event horizon is so large that tidal forces at the horizon itself are relatively weak. You could theoretically cross the event horizon of a supermassive black hole without immediately noticing extreme tides, though you'd still be doomed, unable to escape. When a star wanders too close to a black hole, tidal forces can rip the star apart in a tidal disruption event. As the star approaches, the near side feels stronger gravity than the far side. If the star crosses the black hole's tidal radius, roughly where tidal forces equal the star's self-gravity, the star stretches into a long filament. Part of this filament falls into the black hole while part is flung outward, escaping the system. The infalling material forms an accretion disk, spiraling inward and heating to millions of degrees through friction. This hot disk emits intense radiation, creating a bright flare that can outshine entire galaxies for weeks or months. Astronomers have detected dozens of these tidal disruption events using telescopes that scan the sky for sudden brightenings. Binary stars orbiting extremely close together experience strong mutual tidal forces. In some cases, one star can tidally strip material from its companion. If a compact object like a white dwarf, neutron star, or black hole orbits close to a normal star, tidal forces can pull gas off the normal star's surface. This gas spirals onto the compact object, releasing energy. These mass-transferring binaries produce some of the brightest X-ray sources in the sky. The gas gets so hot as it spirals inward that it emits X-rays rather than visible light. Examples include Cygnus X1, one of the first black holes discovered, which accretes gas from a massive blue supergiant star. Tidal forces also affect the orbits themselves in extreme environments. When 2 neutron stars or black holes orbit each other closely, their immense gravitational fields create ripples in space-time called gravitational waves. These waves carry energy away from the binary, causing the orbit to shrink and the objects to spiral together. The orbital decay accelerates as they approach, creating a runaway process that ends in a merger. The first gravitational waves detected by LIGO in 2015 came from 2 black holes merging after spiraling together. The final moments of the inspiral involve objects orbiting each other hundreds of times per second, experiencing tidal forces that would disrupt any normal matter instantly. These extreme examples remind us that tidal forces are universal, operating wherever gravity varies with distance. From the gentle locking of our moon to the violent destruction of stars near black holes, tidal forces shape the cosmos on all scales. The same mathematical principles apply throughout. Understanding tidal locking in our solar system provides the foundation for understanding these more extreme manifestations, connecting the familiar to the exotic and revealing the unity underlying seemingly disparate phenomena. Part 14: Cultural and Philosophical Implications. The discovery that most planets might be tidally locked to their stars carries implications beyond astronomy and biology. It touches on philosophy, culture, and how we understand our place in the universe. For most of human history, we assumed other worlds would resemble Earth, with similar day-night cycles, seasons, and environmental rhythms. Learning that permanent day and night might be the cosmic norm challenges these assumptions and invites us to imagine truly alien experiences. Consider how fundamental the cycle of day and night is to human culture. Our circadian rhythms evolved to match Earth's rotation. Our sleep-wake cycles, our cultural practices, our mythology and storytelling all revolve around the sun's daily journey across the sky. We mark time by days, we organize societies around diurnal and nocturnal activities, we celebrate dawn and dusk. These patterns feel universal because we've known nothing else. But on a tidally locked world, intelligent beings would develop entirely different relationships with time and light. On such a world, the concept of a day as we understand it wouldn't exist. There would be no sunrise or sunset to mark time's passage. Inhabitants of the Terminator Zone might organize time around other cycles, perhaps the stars' phases if their planet orbits another planet, or weather patterns, or internal biological rhythms unconnected to light. On the deep day side, beings might never have developed vision optimized for darkness, having evolved under perpetual light. On the night side, sight might operate in infrared wavelengths, detecting heat from geological sources rather than visible light. These beings would find our descriptions of sunrise and sunset, dawn and twilight, as alien as we find their world. The fixed position of the star would create a different sense of orientation and navigation. On Earth, the sun's movement provides direction. We speak of going toward the sunset, of east and west defined by sunrise and sunset. On a tidally locked world, the star's fixed position would create an eternal compass. Geography might organize radially around the substellar point or terminator rather than in the cardinal directions we use. Maps might show distance from the bright side or dark side as the primary reference rather than latitude and longitude. Philosophically, tidally locked worlds challenge anthropocentric thinking. We often unconsciously assume Earth's conditions are typical or ideal, the standard against which other worlds should be measured. Discovering that our rotating day-night cycle might be unusual forces us to question what we consider normal. It's a humbling reminder that our experience, while valid, represents only one of countless possible environments. This realization parallels earlier paradigm shifts. When we learned Earth isn't the center of the solar system isn't the center of the galaxy, and our galaxy is one of billions. Each shift decentralized humanity's position and expanded our cosmic perspective. The possibility of life on tidally locked worlds invites speculation about consciousness and perception. If life arose in perpetual twilight, would it perceive time differently than we do? On Earth, our sense of time passing connects deeply to cycles of light and dark, seasons, and change. Without these cycles, would time feel more fluid or static? Would such beings develop clocks and calendars, or would they conceive of time in fundamentally different ways? These questions verge into speculation, but they're grounded in the physical reality that environment shapes perception and culture. Science fiction has explored tidally locked worlds occasionally, though perhaps less than the concept deserves given its likely prevalence. Isaac Asimov's story Nightfall imagines a planet where night falls only once every 2,000 years, creating existential crisis when it finally does. While not tidally locked, the story explores how beings adapted to constant light would react to darkness. More recently, the novel The City in the Middle of the Night by Charlie Jane Anders depicts a tidally locked planet where humans survive in the Terminator Zone between scorching day and freezing night. These stories use tidal locking as a lens to examine human nature, exploring how extreme environments challenge and reveal our values. Looking forward, If humanity ever colonizes tidally locked planets, we'll face profound adaptations. Our biology is tuned to Earth's cycles. Could we thrive without natural day-night rhythms? We might need to create artificial cycles, perhaps living underground with simulated lighting that mimics Earth's 24-hour day. Or we might adapt, gradually adjusting our biology and psychology to the new environment. Such adaptation would mark a new chapter in human evolution, shaping not just our bodies but our cultures and consciousness in ways we can barely imagine. Part 15, Closing Reflections. As we've journeyed through the phenomenon of tidal locking, we've encountered locked moons in our own solar system, explored the physics that creates permanent day and night, speculated about life in terminator zones, and contemplated the philosophical implications. The universe, in its patient mathematical elegance, has created countless worlds where time seems to stand still, where the sky holds one eternal configuration, and where the rhythms of existence differ profoundly from our own. These worlds aren't rare curiosities, but may represent the most common planetary architecture around the galaxy's most abundant stars. The mechanics underlying tidal locking, differential gravitational forces creating friction that steals rotational energy, operate with inexorable patience. Over millions of years, spinning becomes synchronization. The process requires nothing exotic, just time and gravity, two of the universe's most fundamental features. That such simple ingredients produce the strange beauty of mutual locks like Pluto and Charon, or the volcanic fury of Io demonstrates nature's ability to weave complexity from simple rules. Mathematics predicts these outcomes, observations confirm them, and imagination lets us explore their implications. For those seeking life beyond Earth, tidally locked planets present both challenges and opportunities. The extreme environments, permanent day sides and night sides, seem hostile at first glance. Yet life on Earth thrives in environments once considered uninhabitable, in boiling hot springs, in Antarctic ice, and the crushing pressure of the deep ocean. If life can adapt to these extremes on one world, perhaps it can adapt to the extremes of tidal locking on another. The terminator zones, the subsurface oceans, the chemosynthetic possibilities all offer potential habitats. We simply don't know yet. Each new discovery expands our understanding and the range of environments we consider potentially life-bearing. The ongoing search for and characterization of planets around other stars will test these ideas. Future telescopes will map tidally locked planets' temperature distributions, analyze their atmospheres, and search for biosignatures. Perhaps we'll find oxygen and methane together in a terminator zone atmosphere, hinting at life. Perhaps we'll detect city lights on a night side, evidence of technological civilization harnessing artificial illumination. Or perhaps we'll find only barren rocks and frozen wastelands, learning that tidal locking imposes barriers to life we haven't yet imagined. Any outcome will teach us something profound about the universe and our place in it. In our own solar system, missions to Europa and Enceladus might soon explore those tidally heated subsurface oceans directly. Drilling through kilometers of ice presents engineering challenges, but the potential payoff, discovering life that arose independently of Earth in an environment driven by tidal forces, would revolutionize biology. Even negative results, finding sterile water, would inform us about the requirements for life and how often it arises. The process of searching, of pushing our technology and understanding to reach these hidden oceans, drives progress and expands human capability. Tidal locking connects us to the broader cosmos in unexpected ways. When you look at the moon and realize it shows you the same face your ancestors saw, you are witnessing tidal locking's handiwork. When you contemplate that this configuration might be the default for most planets and habitable zones throughout the galaxy, you are grasping a fundamental organizing principle of planetary systems. When you imagine standing on a Terminator zone watching a red sun hang forever on the horizon, you're exercising the same imaginative capacity that drives scientific inquiry and human exploration. These connections, between the familiar and the alien, between the local and the cosmic, enrich our understanding and our sense of wonder. And on that note, we conclude our exploration of tidal locking, of worlds with eternal day and night. From the moon's unchanging face to the possibility of life in permanent twilight zones around distant stars, we've traversed scales from planetary interiors to galactic populations. The physics remains consistent, gravity's patient influence sculpting rotation into resonance. The implications ripple outward, touching astrobiology, planetary climate, and philosophy. As you move forward through your day or night, perhaps you'll look at the moon with fresh appreciation, seeing not just Earth's companion but a window into the dynamical processes shaping worlds throughout the universe. Thank you for joining me on this cosmic journey. Until next time, keep looking up and keep wondering.